Hi Bobcats! In this video we're going to take a look at how you calculate the oxidation number on an atom in a compound. And for this part of the video we're going to look at a couple of relatively straightforward examples. The next video is going to take a look at some more complicated examples. Our objective is simply to develop the method to calculate the oxidation number on an atom. And as I said on the last slide, we'll work a couple of straightforward examples and save the complicated examples for the next video. When we write chemical reactions, we don't normally show how electrons get transferred from one species to another. We don't normally show something like plus electrons or on the reactant side or plus electrons on the product side. So what we're going to use to track how those electrons are getting transferred from one atom to another is this formalism known as oxidation numbers. And so it really is just an electron bookkeeping tool so that we can keep track of where the electrons are. Conceptually, you can think of it as the charge that an atom would have if the bonding were 100% ionic. So if we're going to basically assign every bonding electron to one atom or another atom. And as we go through and do this assigning process, if we're assigning an atom more electrons than its number of valence electrons, then it has extra electrons for these purposes and it'll have a negative oxidation number. But if this assignment process gives an atom fewer electrons than its number of valence electrons, then since it's missing those electrons, it'll have a positive oxidation number. That previous slide had the theory. Here's how to think about oxidation numbers. This slide has the process, the practical step-by-step procedure. So first of all, if you have an element in its elemental form, it has an oxidation number of 0. So as an example of something that's an element in its elemental form, if you have gold, which has the symbol AU and it's a solid, well, that's its normal stable elemental form. It has an oxidation number of 0. If you have a monatomic ion, its charge is its oxidation number. So for instance, if we have something like a group 2 ion, like calcium +2, then its oxidation number is +2. If we have something like a halogen, like bromine, which has a -1 charge, then -1 is that bromide ion's oxidation number. When hydrogen is involved in a compound, its oxidation number will be +1. When oxygen is involved in a compound, its oxidation number will be -2. When fluorine is in a compound, its oxidation number will be -1. Now it's real key to remember on these three elements that it's when they're in a compound. If you have simply O2 in the gas phase, that's the elemental form, and the first rule applies, which is that its oxidation number is 0. So when oxygen's in a compound, we're going to call it -2. Now, that's great if we only have to deal with hydrogen, oxygen, and fluorine, but most compounds are going to have a lot of other elements in them. So here's how we figure out the things that we don't have a rule for. The sum of all of the oxidation numbers in a compound has to add up to 0 if it's a molecule. And if we're talking about a polyatomic ion, the sum of the oxidation numbers has to equal the charge of that polyatomic ion. So here are a couple of examples. We've got chlorine, Cl2. Well, this is an element. This is the elemental form. This is chlorine all by itself, and it's a Brinkelhoff, so it has the subscript of 2 on it. So this is the elemental form, so that means that its oxidation number is 0. Now in this next compound, HCl, we've got a hydrogen atom and a chlorine atom. We have a rule for hydrogen. By rule, hydrogen, when it's in a compound, is +1. And we know that the oxidation numbers on all of the elements have to add up to give us 0. So if hydrogen is +1, then chlorine has to be a -1, because then +1 plus a -1 gives us 0. So the oxidation number on hydrogen here is +1, and the oxidation number on chlorine is -1. Our method that we developed here was that if you have a pure element in its elemental form, its oxidation number is 0. If you have an ion like sodium +1, then its charge is its oxidation number. And if we have hydrogen, oxygen, or fluorine in a compound, they'll have oxidation numbers of +1, -2, and -1, but again, that has to be while they're in a compound. And last but not least, if we add up all of the oxidation numbers, it's going to be equal to 0 for a neutral compound, or it'll be equal to the charge for a polyatomic ion. There we go, the charge for that polyatomic.